Today we're going to start with industries based on nitrogen. The first industry is going to be ammonia manufacture from the combination of nitrogen and hydrogen according to the equation shown right here. The optimum conditions for this reaction are very high pressure and the lowest possible temperature, which is typically between 400 and 500 degrees Celsius. The limit of the applied pressure is determined by the cost of compression, and it's typically between 100 and 1000 bar. And the reaction can be shifted further to completion by the removal of the produced ammonia from the reaction medium. The reaction is conducted over the surface of a catalyst that is mainly an iron catalyst with around an 80% iron on a support composed of these oxides shown right here. Alumina, silica, calcium oxide, and magnesium oxide are mainly promoters to inhibit sintering or crystallization of the catalyst and to increase the surface area of the catalyst. Calcium oxide also helps preventing poisoning of the catalyst, while potassium oxide increases the activity of the catalyst. The catalyst is typically prepared by melting a mixture of iron oxide with promoters at around 1500 degrees Celsius in an electric furnace, followed by a rapid cooling, pulverization, and sieving step. And this step, the optimum particle size is typically between 6 and 10 millimeter in size. And the second step is a subsequent reduction, which is carried out in the pressure reactor in the ammonia plant itself at moderate pressures between 70 and 300 bars at temperatures between 350 and 400 degrees Celsius. During that step, a highly porous iron is formed on the surface of the catalyst. A high gas flow is required in this step to ensure low water and prevent aging of the catalyst. Ammonia catalysts are very pyrophoric. However, they can be stabilized by exposure to nitrogen containing 0.2% oxygen at 100 degrees Celsius to form a more stable partially oxidized form that can then be easily reduced in the ammonia reactor itself due to the reducing effect of the hydrogen gas. This catalyst is extremely sensitive to poisons. Therefore, gaseous compounds containing oxygen, sulfur, phosphorus, chlorine have to be removed from the precursors. In some cases, poison catalysts can be reactivated by reduction with pure synthesis gas. However, if the poisoning is due to sulfur, phosphorus, arsenic compounds, regeneration is not possible. Also, hydrocarbons and inert gases such as argon sometimes interfere with the process, so they need to be minimized as much as possible. This is a flow chart that summarizes the process. 3 precursors are used in this process: air as a source of nitrogen and the mixture of methane and water. In a steam reforming step, it's going to produce hydrogen and carbon monoxide, then mixed with nitrogen from air. And the mixture is then put through several steps of converting carbon monoxide to carbon dioxide and complete removal of both carbon monoxide and carbon dioxide, producing a synthesis gas, which is basically a mixture of hydrogen and nitrogen that goes to the reactor itself containing the catalyst and goes through cycles of reaction, separation, and so on to achieve the maximum conversion possible to produce the highest yield of ammonia. As we said, the raw materials for this process are simply nitrogen and hydrogen, and typically if the reaction is conducted at 0 degrees Celsius and 1 bar, 2400 cubic meter of hydrogen combined with 800 cubic meter of nitrogen would produce 1 ton of ammonia. And as we explained, nitrogen is taken from air by low temperature fractioning of air, and hydrogen is produced from hydrocarbons or coal and water in a steam reforming process. It can be produced from natural gas, basically methane or naphtha, or from crude oil products like heavy heating oils, or from coal through the coal gasification process by partial oxidation. The choice of the process depends on the availability and prices of these raw materials. The first step of producing hydrogen is a steam reforming process from natural gas or naphtha. The precursor is reacted in the presence of catalyst at around 700 to 830 degrees and 40 bar in an endothermic process with steam in a steam reforming process in which the hydrocarbon and water would convert to carbon monoxide and hydrogen. The catalyst used in this step is nickel oxide immobilized on alumina or magnesium oxide immobilized on alumina spinels. This catalyst is very susceptible to poisoning by sulfur and halogens as well as arsenic compounds. Therefore, the precursor of natural gas or naphtha has to be desulfurized using cobalt or nickel or over molybdenum oxide catalysts under hydrogen in order to reduce sulfur containing compounds into H2S that can then be absorbed on the surface of zinc oxide. After the desulfurization process, steam is added to the mixture and heated to 500 to 550 degrees Celsius before it's fed into a primary reformer. And the gas leaving the primary reformer contains around 7 to 10% methane, which has to be removed in a secondary reformer by partially burning with air within a nickel catalyst filled shaft furnaces at around 1000 degrees Celsius. The quantity of air is adjusted to give the nitrogen to hydrogen ratio required for the stoichiometric reaction producing ammonia. Second step is oxidizing carbon monoxide to carbon dioxide using steam, producing further amount of hydrogen. This step is conducted over iron oxide, chromium oxide catalysts or copper oxide, zinc oxide catalysts. The iron oxide, chromium oxide mixture typically requires higher temperature and is less efficient in the conversion. However, it's not sensitive to sulfur containing raw materials. So the copper oxide, zinc oxide catalysts operate at much lower temperatures and is much more efficient. However, it's very sensitive to sulfur. So the raw materials have to be sulfur free. The third step is carbon dioxide and H2S removal by adsorption in methanol, propylene carbonate, or N-methyl pyridone at high pressures. Oxygen containing impurities can also absorb into zeolites to remove water or scrubbed using liquid nitrogen at around negative 190 degrees Celsius and 80 bar to remove any traces of carbon monoxide, carbon dioxide, and so on. And the final step of purification to remove any traces of carbon oxides through the reduction with hydrogen in a methanation step. So here is a more detailed flow chart for the process where the water is first converted to steam and then mixed with natural gas, then injected into a primary reformer to convert to carbon monoxide and hydrogen. On the other hand, air is fractionated to obtain nitrogen and then mixed with the primary reformer gas into a secondary reformer. The obtained gas mixture is then injected into a carbon monoxide converter with several stages to convert it to carbon dioxide. And then the gas mixture is taken into a gas purification step to remove carbon monoxide and carbon dioxide, followed by successive carbon dioxide absorbers to remove any traces of carbon dioxide. And the pure synthesis gas is then compressed and injected into the ammonia converter to produce ammonia. As we said, the optimum temperature and pressure for the process has to be optimized. In the first plot right here, it shows the percent yield of ammonia production as a function of pressure at constant temperatures. And the second plot here shows the percent yields as a function of temperature at constant pressures. And you can clearly see that there is an inverse effect between the two parameters. So for the optimum yield, we need to have higher pressures and lower temperatures. Ammonia is a major precursor for a lot of other commodity chemicals, especially in the fertilizer industry, of the production of ammonium phosphate, ammonium nitrate, urea, and other types of fertilizers. And it's also a precursor for the production of nitric acid, which is a major reagent in a lot of organic transformations.